So we've looked at the ideal gas equation. Now let's consider some examples of using the ideal gas equation. So this question reads, a gas of volume 2 liters, pressure 3 atm, and temperature 300 Kelvin expands to a new volume of 3 liters at a pressure of 4 atm. What is the new temperature of the gas? So first, let's state our variables. So this has a volume of 2 liters, pressure 3 atm, and it has a measured temperature of 300 Kelvin. It expands to a new volume of 3 liters, a pressure of 4 atm, and a new temperature of, well, we don't know what the temperature is, so that's what we're trying to find. Okay, now we know the relationship from previously. It's PV over T is a constant, which means that in this new situation, P1 V1 over T1 is equal to P2 V2 over T2. Okay, that's our equation. We have some known and unknown quantities. Let's substitute them in. Now, most of the units are exactly the same, so there's no conversions that need to be made. And so what I'm going to do is just not include the units in the equation, because we know that the temp T2 should have units of Kelvin. So substituting in numbers, 3, should put, what I'm going to do is actually these situations. So V1, P1, T1, V2, P2, T2. So this is the first situation. And then we have it expands, the gas expands, and we get the new situation. So these are where these variables come from. So we have 3 times 2 over 300 is equal to 3 times 4 over some unknown, T2. So if we simplify this, I want to isolate 1 over T2. So 1 over T2 by itself. On the other side of the equation, I'm going to divide both sides by 12, and what I get when I do that is 2 over 1200. Okay, flipping T2 to solve for T2, it's just 1200 over 2, which gives you an answer of 600 Kelvin. Okay, so somewhat straightforward. Once you have the equation, you substitute numbers in and you just solve for T2. Okay, now let's try another example. Figure 3.16 shows two curves obtained in an experiment to investigate the dependence of pressure on temperature at a constant volume. Okay, so temperature and pressure changing, this volume is constant. Which straight line corresponds to the larger volume? Both curves correspond to the same number of moles. Okay, so how exactly are we going to sort out this question? Well, let's start with the ideal gas equation. PV equals nRT. So we know that PV, we know that it's at the same number of moles. The gas constant is the same. So PV is proportional to the temperature. Now we know that down this line, okay, this line right here corresponds to a constant temperature. So the volume is constant, the temperature is constant. What do we know about, so which one of these, so yeah, the volume is constant in each of these, the temperature is constant, so which one of these has the higher volume? Well, we know PV is proportional to T, and 4, so if we want T to remain constant, okay, and we know that the volume in each of these situations is constant, so as P increases, from this equation, T is constant, P increases, I'm going to put this, so P increases, V Well, V has to decrease for T to remain absolutely constant, the same number. So the volume must decrease. Therefore, C has a higher volume because P is low, so P is the lower, and V is a higher volume. So P decreases, V has to increase. Okay, and therefore C has a higher volume. Alright, so it all has to do back to the proportionality and the relationship between the variables P, V, and T. Let's try another example. This is very similar to the first one we did. So, a fixed mass of an ideal gas has a volume of 870 centimeters cubed at a pressure of 1.00 times 10 to the 5 pascals and a temperature of 20 degrees Celsius. The gas is heated at constant pressure to a temperature of 21 degrees Celsius. Calculate the change in volume of the gas. Okay, so first, let's list our variables. P1, very similar to before, P1, V1, T1. So the initial pressure is 1.00 times 10 to the 5 pascals, which is just atmospheric pressure, as a volume of 870 centimeters cubed, and a temperature of 20.0 degrees Celsius. So let me just erase this. 20.0 degrees Celsius. The gas is heated at a constant pressure, T2, P2, constant pressure, so the pressure is exactly the same, 1 atmosphere, 1.00 times 10 to the 5. To calculate the change in volume, well, we don't really know that, but we do know that the temperature changes to 21 degrees Celsius. So, let us use this relationship once again. P1 V1 over T1 is equal to P2 V2 over T2. Substitute in our known quantities. Now, P1 and T2 are exactly the same. So if we were to write, we could just change this to P1. Okay, so P1 is exactly the same as P2. They're completely equal. And so it makes it convenient for us, because what we can do, since we know that the two quantities are exactly the same, is they're just going to cancel each other out. If we divide both sides by P1, that term completely cancels out. So we don't have to worry about that. We have much fewer variables to work with. Okay, so let's write this out. We have V1 is 870 divided by T1, which is 20.0. Once again, I'm not including the units because all of the units are exactly the same, so we know that our final answer is going to have units of centimeters cubed. Equals V2, we don't know what V2 is yet, and T2 is 21.0 degrees Celsius. Isolating, so multiply both sides by 21 degrees Celsius, we get V2 is 870 times 21.0 over 20.0, and that gives us a final answer of 913.5 centimeters cubed. And if we want to round that to the lowest number of significant figures, this is considered 3. So we'll say it is 3 significant figures, because these are all, let's say these zeros were all measured values and not rounded. So if we round that, we get a number of 914 centimeters cubed. Okay, very similar to the first equation, the only thing is there's a constant term, so they cancel out. The last problem. Now this problem, we have an ideal gas held on a cylinder by a movable piston. The pressure of the gas is P1, its volume is V1, and its Kelvin temperature is T1. Situation right here. The pressure, volume, and temperature are changed to P2, V2, and T2 respectively. The change is brought about as illustrated below. So P1 V1 T1, P2 V2 T2. Now what we have in this situation is the volume remains constant. The pressure moves to P2, and the temperature, if I can just erase this, the temperature goes to some intermediate value, T prime. So it's heated at a constant volume to pressure T2 and temperature T2, and then it is heated at constant pressure. So at first we keep the volume constant, then we keep the pressure constant to volume T2 and temperature T2. So state the relation between P1, P2, T1, T prime, and V1, V2, T prime, T2. Now I'm going to leave this to you to try on your own, but keep in mind the ideal gas equation, PV equals nRT, and all of the three equations. Now it says use your answers. This question is a bit challenging and it's worth 4 marks, so it requires a bit of work. This question says use your answers to B, this question, these right here, to deduce that for an ideal gas PV equals KT, which is just a formulation of the ideal gas equation, where K is constant. The important thing to remember when solving this equation is that both of these equations have T prime in common. And so if you solve for T prime, okay, the T prime is what connects these two equations. And so T prime will give you an equation that can equate these two, okay? It's the intermediary between this state and this state. Okay, and once you use that fact, that T prime is the intermediary, you can basically equate two of the relationships you get and get the final answer, which is exactly this. Okay, so I'll let you try that on your own. If you have any questions, you can just come talk to me, but I'm going to leave that one to you to try on your own. Okay, so those are some examples. Hopefully that clarified how to use the ideal gas law to solve real-life situations.